Today we're going to be looking at the kinetic molecular theory. So what is the kinetic molecular theory? Well, kinetic comes from these two Greek words, both having to deal with movement. Molecular comes from Latin molecula, meaning tiny mass, which means particles in this case. So putting those words together, kinetic molecular means movement of particles. So the kinetic molecular theory is a theory that deals with the movement of particles. And there are a few variables or aspects of the kinetic molecular theory. These are extremely important to know. So first we got temperature. Temperature is defined in this theory as the movement of particles. Volume is the space taken up by the said particles. Pressure is the collisions between particles and the surrounding. So let's say the particles are in like some container or something. Pressure would be like the amount of collisions between those particles and the container. And moles is obviously, as we learned in the previous unit of stoichiometry, the amount of said particles. So there are a few laws that deal with relationships with variables in the kinetic molecular theory. First, we have Boyle's law. So when you are dealing with changes in volume and pressure at a constant temperature, meaning changes in the space taken up by the particles and collisions between particles and surfaces at the constant temperature, means the constant speed of the particles. Boyle's law basically says volume and pressure are inversely proportional, and this graph basically shows it. This is an inverse proportion graph. Inversely proportional means as one goes up, one goes down. As one goes up, one goes down, and as one goes down, the other goes up. Meaning, if volume increases, pressure decreases. Volume decreases, pressure increases. So this can be represented by this equation. P1, which stands for pressure 1, times V1, stands for volume 1, is equal to pressure 2 times volume 2. So this is pressure at one point. I think this is before and after. So pressure before, volume before, pressure after, volume after. Let's look at an example. A sample of oxygen gas occupies a volume of 250 milliliters at 740 torr pressure. The volume will occupy at 800 torr pressure. Torr is unit pressure, by the way. Comes from the scientist Torricelli. So we first got to get our equation. So we are dealing with volume and pressure given nothing else, which means we should probably be using Boyle's because we don't know the temperature. We're going to assume that it's constant. So you get our formula, P1V1 equals P2V2. And now we're going to substitute our information into the formula. So it occupies volume 250 milliliters at 740 torr pressure. That is before. It's occupying it right now. Okay? So we got 740 torr and 250 milliliters as P1 and V1. Then it says the pressure is going to change to 800 torr. So we're going to put 800 torr as P2, and we're going to leave V2 as V. That's the thing we're trying to find. So we've got one variable that we're going to try and find. Now what happens when you have a bunch of values, but you have one variable that you're trying to find? What is this called? You said algebra. You're correct. We're going to use simple algebra. So we're going to try and isolate the variable by dividing both sides by 800 torr. So that becomes 740 torr times 250 milliliters divided by 800 torr. The torr cancels out, which means that what we're going to end up with is going to be milliliters. And we put this in the calculator. That becomes 231.25 milliliters. So that means at 800 torr pressure, we're going to have 231.25 milliliters of volume. So what has this to do with Boyle's law? So this fits Boyle's law as when the pressure increased, it's at 740 torr to 800 torr. So that means pressure increased, it went up. The volume decreased. It became 250 milliliters to now 231.25 milliliters. So as pressure went up, 740 to 800, volume went down. 250 to 231.25, which is what we're trying to find. That proves Boyle's law. Now we've got another law. Charles's law. So when given changes in volume and temperature at a constant pressure, which means that pressure is out of the equation right now, it's going to stay constant. So changes in volume and temperature. So volume, remember, is space taken up. Temperature is a speed. So Charles's law states temperature and volume are directly proportional. It's shown by this graph right here. As you can see, it's linear. It goes straight up, which means as one goes up, the other one also goes up. One goes down, the other also goes down. So as volume decreases, the temperature goes down, which means particles move slower. As volume increases, temperature also increases, which means molecules move faster. It can be shown by this formula. Don't care about this bit right here. It is true, but like it's gonna be a little bit more confusing. I think it's V1, that means first volume, before volume, or I should say, before volume and over before temperature, and then after volume over after temperature. Now, here's the thing with temperature. In every single formula, every single time, they only use a unit of temperature called Kelvin. You cannot use Celsius, you cannot use Fahrenheit. So to convert Celsius to Kelvin, you need to simply add 273 to the value given in Celsius. Let's use an example. A sample of nitrogen occupies a volume 250 milliliters at 25 degrees Celsius. What volume will it occupy at 95 degrees Celsius? So we got the formula dealing with volume and temperature. And then we first have to change Celsius to Kelvin. Look, we're given 25 degrees Celsius, 95 degrees Celsius. But we can't input 25 and 95 into here, because this formula only works in Kelvin. So we're going to add 25 and 273 together. Let's remember, that's the formula, C plus 273, and 95 and 273 together. Which gives us 250 milliliters, remember, volume 1 over temperature 1, which is now in Kelvin, 298 K, is equivalent to volume 2, which is what we're trying to find, so that says V as V, and then over 368K, which is what is a conversion of 95 degrees Celsius to Kelvin. Now, simple algebra again, we're going to cross multiply, so that goes there, that goes there. Then we're going to divide 250 times 368 over 298. K's cancel, which is the answer going to be left is milliliters, and the answer becomes 308.72 milliliters of volume. This fits Charles' law because when the temperature increased 25 degrees Celsius to 95 degrees Celsius, or in terms of Kelvin, 298 Kelvin to 368 Kelvin, the volume also increased 250 milliliters, 308.72 milliliters. Then we're going to changes in all of them, volume, pressure, and temperature. We're going to use what's called the combined gas law. Volume increases, pressure decreases, temperature increases. Volume decreases, pressure increases, temperature decreases. Basically, these are going to explain the relationships, but remember, they will not always be true. It depends on what the question is asking or how it's worded. I'll show you an example in the future. And the formula for this is P1, so for before pressure times before volume over before temperature equals before pressure before volume over before temperature. Now remember these two laws before? P1, V1, P2, V2. Notice how they're very similar to this one. It's just that in Boyle's law, temperature was not there, so we just cut off the bottom, it was only this. And in Charles's law, pressure was not there, so it was only V1, T1 and V2, T2. Coincidence? I think not. Now let's look at an example. But I think I am not going to do this one. I'm going to have a special guest do it for us. And he's going to explain it to you in a better way.
Okay, so we have this problem that gives you three variables in the beginning. So we get the volume, which is 0.95 liters of a gas, and we get the pressure, which is 1.08 atmosphere, and we also get the temperature, 48 degrees Celsius. Then we get two variables, so we get 1.20 liters, which is volume, and temperature, 64 degrees Celsius, which is, just the temperature. So the question is asking you to calculate the pressure, right? So we can substitute in the units into the combined gas law equation, but first we need to convert all the Celsius for the temperature into Kelvin, because that's how Mr. Hicks wants you to solve it. So the formula to converting Celsius into Kelvin is basically you take however much Kelvin you're given. So if I'm trying to convert this to Celsius, I'm going to want to add 273 to that. So 48 plus 273 is 321 Kelvin. So that's what we're going to use. We're not going to use Celsius. So we need to do that for 64 as well. So 64 plus 273 is 337 Kelvin. So this is what we're going to use in our equation. So now the question is asking us to calculate the pressure of the same amount of gas in the container, which it gives you the volume, and the temperature, which it gives you. So we've already calculated what the Celsius is in Kelvin. Now we already figured out what we're finding or what we're calculating thanks to the question saying calculate the pressure. But we were already given the pressure in the first part of the question. So that is going to go into P1 because that is the first pressure we are given. So the 0.95 liters will also go into V1 because that is the first volume we are given in the equation. The same thing applies for 48, which we figured out was 321 in Kelvin. So that will go into T1 in the gas law equation. Then we do the same thing for the second part. We don't know what the pressure is because that's what they're asking us. So we'll just leave that as P or P2. We know what the amount of gas is, or the volume, which is 1.20 liters. So that is going to be our V2. And then we have a temperature of 64 degrees Celsius or 337 degrees in Kelvin. So that's going to be our T2. So what do we need to find? We need to find P2. How do we solve this when we plug in all the values into the ideal gas law? So basically, this is just basic algebra. You have to substitute the variable for P, and once you do that, you can solve. So it's done over here. 1.08 atmospheres times 0.95 liters times the 337 degrees, which is of Kelvin. That came from this part of the equation. We now multiply it on the other side because remember, we are substituting this variable here of P2. Then we see we have 1.20 liters, which is the volume, and we have 321 degrees in Kelvin, which is T1, which is temperature. P is still not alone, so we have to move this to the other side again to isolate the variable. We can see that this is multiplying into P, so we have to do the inverse of that, which is division. So we put that on the other side. And now you just plug it into your calculator, all these values, and you will get the answer.
Alright, so now we have looked at the relationships between variables. Ruche explained the combined gas law to us. I explained to you the Charles and Boyle's law. All three of them are going to be used to find these relationships. Remember, Charles and Boyle's are only when at least one thing remains constant. So for Boyle, it's when Boyle is when temperature is constant, and Charles is when pressure is constant. And we've looked at all their relationships. What else can we do? Well, unfortunately, stoichiometry. Stoichiometry is going to make a comeback. Unfortunately, yes, stoichiometry is coming back. If you didn't remember, stoichiometry is to do with moles. So that's exactly what we're going to do in this next part. So the person that came up with the idea of the mole and people built off of him, his name was Avogadro. He came up with the law that said moles and volume are directly proportional. Moles has to do with the number of particles, remember? Which means more particles is more volume, less particles is less volume. Remember, directly proportional? If one goes up, so does the other? Well, same thing is going to apply to moles and volume. And we get this thing called the molar volume. This is the basic formula. 1 mole of a substance is 224 liters of that substance. So 1 mole is 224 liters, and 224 liters of a substance is 1 mole. However, this is not always true. This is only true at STP, standard temperature and pressure. STP is when the pressure is only 1 atmosphere, the temperature is 0 degrees Celsius or 273 degrees Kelvin. This is only true in those conditions. If they specify pressure and if they specify degrees, then it is most likely not a STP. It has to be either 1 in 0 or 1 in 273. Let's look at an example. So we got a chemical reaction here. Nitrogen plus 3 hydrogen goes and synthesizes into ammonia. So the question is, how many liters of hydrogen gas will be required to react with 7.6 liters of nitrogen gas at STP? So at STP, by saying these two words, we already know these two parts. Okay? So the formula is not going to, there's no formula for this. Now we go back to good old dimensional analysis. So first we're going to convert these liters to moles. Remember from stoichiometry, we convert everything to moles first. If it is in grams, then you also convert to moles by using the molar mass. So how many moles of nitrogen? So 7.6 liters of nitrogen, and then 1 mole. 224 liters is 1 mole, remember? STP. And that equals 0.34 moles of nitrogen. Then we get the molar ratio to try and find out the other element. Remember, for stoichiometry, molar ratio is a key bit. So how many moles of hydrogen do we now have? Well, we take this answer, then we use a molar ratio, 3 from there, 1 from there, and we get 1.02 moles of hydrogen. So we know that 1.02 moles of hydrogen are going to be used in this reaction. Now we just need to convert that back to liters. So we use this thing again, 1.02 moles of hydrogen, convert that, moles cancel, liters at the top, and we get 22.84 liters of hydrogen. So 22.84 liters of hydrogen are going to be required to react with 7.6 liters of nitrogen gas at STP, only at STP, remember. Now, what are not STP? Well, unfortunately, there's a formula for that. It is called the ideal gas formula, and this is unfortunately also the majority of how real life is going to be. The formula goes PV equals nRT, or PVNRT. So P, as we know, stands for pressure, V stands for volume, N stands for the number of moles now, and then T is temperature, and R is a constant called the ideal gas constant or the universal gas constant. It is 0.0821. R is 0.0821. Now, the ideal gas formula only works with these units. Pressure must always be in atmospheres. Volume must be always in liters. And obviously, temperature must be in Kelvin, always, and literally all the time in every formula. And N is moles. Moles doesn't have a specific unit other than moles, so just leave it as that. Here's an example. If I have an unknown quantity of a gas at a pressure of 1.22 atmospheres, a volume of 31 liters, and a temperature of 87 degrees Celsius, how many moles is that? Notice how they did not mention STP anywhere in this question, which means you're going to have to use ideal gas formula. I'm going to input in 1.22 atmospheres for pressure, since this only P must be in atmospheres, that works. 31 liters for volume. And then N is what we're trying to find, so moles of gas, because we're going to leave that there. R we know is 0.0821. And temperature we're going to convert to Kelvin. 87 plus 273 is 360 degrees Kelvin. So now we got this. 1.22 atmospheres times 31 liters equals N, and then times 0.0821, which is our universal gas constant, times 360 degrees Kelvin. Then we're going to solve for the unknown, divide both sides by this, put that into the calculator, and we get 1.28 moles of gas. So if you have an unknown quantity of gas at a pressure of 1.22 atmospheres, a volume of 31 liters, and a temperature of 87 degrees Celsius, you are going to have 1.28 moles of that gas. We want to thank you for watching from both of us, and see you later.